Alright, now that we have understood how to find the magnitude of EMF in case of motional EMF, and turns out that magnitude of EMF was BLV, right? In this case at least. So magnetic field is B, length of the rod CD, which is sliding to the left with the velocity of V, turns out to be BLV. Now the question that remains to be answered is what's the direction of this EMF, right? And for that we are going to use Lenz's law once again. And going through the four basic steps. What are those? First is to identify the original magnetic field's direction, then finding out if the flux associated with the loop, whether it is increasing or decreasing, right? So whether it is increasing or the flux is decreasing. And third thing is to identify, based on the first two steps, we'll identify the direction of induced magnetic field. That is to induced magnetic field will always be such that it tries to oppose the changing flux. And based on the third step, so basically based on the first two steps, we decide what the direction of BI is going to be, and based on the direction of BI, the induced magnetic field, we are going to decide the direction of current. And once we get the direction of current, it's like as good as getting the direction of EMF. Let's try doing this to get the direction of current in the loop ABCD. Obviously it is one of the two things. It is either going to be clockwise or anti-clockwise, right? So it's either going to be clockwise or anti-clockwise. So, but we still need to decide which one it is, and obviously through that we will also be learning more about Lenz's law, right? Fine. So first thing, identify the direction of BO. That is pretty simple in this case. Magnetic field BO, original magnetic field which is causing the induced EMF, is actually inside all these bunch of crosses, white crosses you see. That's the direction of magnetic field. Alright, now that we have established that, next step is to identify whether the flux is increasing or decreasing. Now look at this, ABCD, the loop, and looks like the velocity of the rod is to the left. If it was to the right, maybe the story would be something else. But right now, the situation we have considered, the rod CD, which is also a conductor, is sliding to the left. And with this rod sliding to the left, the area, this area right here, this entire area ABCD actually is decreasing. And if the area decreases, the flux also decreases. So flux actually is decreasing. Alright. So magnetic field is inside and the flux is decreasing. Now the moment the flux decreases, the induced magnetic field tries to avoid that. Meaning, while the given situation is such that the flux is decreasing, what happens is the induced magnetic field will try to increase it. Meaning, it will in fact try to support the original magnetic field in this case, because the flux is decreasing. Now that the flux is decreasing, the induced magnetic field will also be in the same direction as the original magnetic field. That means the induced magnetic field, I'll just write the direction of induced magnetic field with this color, this purple color here. Induced magnetic field in this case also should be inside. Okay, now that the third step is established, that the induced magnetic field should be inside, for that to happen, for the induced magnetic field to be inside the plane of the screen, what should be the direction of current in ABCD? Look at ABCD more like a loop for that, right? It's pretty easy that way. If you look at ABCD more like a loop, then obviously with the right hand rule, the direction of current has to be like this in ABCD. It has to be clockwise in this case, and therefore to answer this question, the direction of EMF is going to be clockwise, at least in this case. Now quickly, if the rod CD were moving away from AB, maybe if the rod CD, I'll just draw it here, if the rod CD were moving in this direction, let's say to the right, then the flux would be increasing. And to avoid that increment of flux, BI would have been outside. BI would have been outside. And for BI to be outside, the current should have been anti-clockwise. That's a different story. There are different cases you can, go through. But right now, for the given situation, this situation right here, the flux should actually be, the current should be clockwise. Alright, now that the current is clockwise, then how do I decide the direction of EMF? I've not done that yet, right? So let's try to focus on that. So in order for current to go like this from D to A, from A to B, and then B to C, CD actually is the source of EMF, kind of source of EMF, right? So it's as if this the CD section of the diagram is behaving as if there is a battery fixed like this, with D at higher potential, and C to be at lower potential. Delhi is at higher potential, and C for Chennai is at lower potential, right? This is the negative side and this is the positive side. If you are, for all you care, remove this CD and put instead of that a battery like this with the negative, with this being the negative end and the longer one being the positive end. If you fix that again, then the current will be in the same direction as these purple arrows are indicating along ABCD, right? So that's how you identify the direction of EMF, provided you don't know something called Fleming's left hand rule. Fleming's left hand rule. If you know that, then you don't have to go through all these processes in order to find the direction of EMF. Fleming's left hand rule actually makes it quite simple. Establishing the direction of EMF, it makes it very simple. The Fleming's left hand rule, we'll discuss that. All right, yeah. So Fleming's left hand rule, as the name suggests, requires you to use your left hand. All right, and I've tried to draw something over here. So according to Fleming's left hand rule, if you want to identify the direction of current in case of motional EMF, that is in case of motional EMF, you need to use left hand, something like this. Pretty simple, right? So first of all, hold 3 fingers, that is thumb, index finger and middle finger of your left hand mutually perpendicular to each other, something like this, as you see in the diagram. If the thumb is in the direction of velocity, magnetic field is in the index finger is in the direction of magnetic field, then the middle finger gives you the direction of current. That's how you use Fleming's left hand rule, right? So thumb basically is in the direction of magnetic field. I'm sorry. Thumb basically is in the direction of velocity of the rod. Index finger is in the direction of magnetic field, and with these two you have to first make sure that velocity and magnetic field are in the direction accordingly, and then finally whatever the direction your middle finger is pointing at becomes the direction of current. All right, so I hope you understand that. And if Fleming's left hand rule mostly is to be according to me at least, Fleming's left hand rule, use this only to answer the very Fleming's left hand rule question, as in if they end up asking you in your tests what is Fleming's left hand rule, only to answer that know these things. Otherwise Fleming's left hand rule as such is not really you don't really have to remember that in order to answer this question, the question of identifying the current, that you can do using basic Lenz's law. I agree that it's going to take longer time, but that is one memory less for you to but yeah, for competitive exams and all, obviously remembering things like this helps. It helps saving time. All right, so yeah, choice is yours. So that's Fleming's left hand rule for you. Now for the main discussion of this, the heading, I've been hiding it for a while now. Origin of EMF. So we have established this EMF, right? We have also found the direction of EMF. Turns out that the EMF is equal to BLV. Everything seems to be working out quite well. Except let's try to look at this whole situation in a different perspective. Maybe try to answer this in terms of the basic electrostatics and magnetism. Actually, that's what we have been doing here, but let's take a different approach. Let's try that. So what I'm going to do is I'm going to zoom in this region, this region right here, the rod you see, CD rod, and notice everything else is going to be same. That the rod, I'm only zooming this region, everything else is still the same. That is, magnetic field is still inside, velocity is still going to be towards left, and rod is going to have length L. And then we see we're trying to answer with all those things, we're trying to answer the direction of EMF and the establishment of current, all those things. Maybe we'll take a different approach and we'll try that. All right, so let's see how that works. So I have, let's say, I'm going to zoom out the CD version of the rod, right? So let's say I have this rod right here. I'm only zooming that region. Let me choose a little longer. There goes the rod CD, right? So this end of the rod is obviously C, and this end of the rod is obviously D. This is D, that is C. All right, and notice everything else that we need to have here. That is, there is this entire region where the magnetic field is actually directed inwards. So this is going to be direction of magnetic field throughout the journey of the rod. Number one, magnetic field is going to be inwards, as it was in this diagram. All right, so magnetic field is inwards. What else did we have? We seem to be having velocity to be in this direction, right? So velocity, the rod was in this direction. We are going to again have velocity in that same direction. So velocity of the rod is in this direction. All right, and rod, remember, is a conductor. Since it's a conductor, I'm thinking the rod CD has a lot of free electrons. It has got a lot of free electrons it has got, right? So let's say one such electron, I'm focusing on that. So one such electron is this right here. So this is one such electron. It is free, remember. So if somehow you can apply force on this, it will definitely move. All right, let's focus on the journey of this electron. I'm thinking the electron that you see right now here in the diagram, this one, actually there are a bunch of electrons which are free, but I'm focusing only on this electron. Looks like this electron, while the rod CD is moving towards left, the electron also is moving towards left. All right, so with the electron moving towards left, electron, don't forget that it's a charge, right? So if the electron is moving towards left, or a charge moving towards left, perpendicular to magnetic field. Wait a second, I think that reminds us something, doesn't it? We'll go back to motion of a charged particle in the region of magnetic field. Let's say I have a region of magnetic field. That magnetic field is like this, which is the situation, which is pretty much the situation over here in the present diagram. Looks like magnetic field is actually inside, right? So I have a region where the magnetic field is inside. I have an electron which is in fact moving in this direction. The electron is actually moving in this direction. Oh wait, with this I'm thinking the electron is in fact going to experience a force in this direction. The force experienced by the electron, that will be the force experienced by a positive charge. If you do the right hand rule, if you do the expression for force, F is equal to the magnetic force, I hope you remember, Q into V cross B. If you use this expression to find the direction of magnetic force, V cross B is going to give the direction of magnetic force, right? So V is in this direction, B is inside, so V cross B, if you use the right hand rule, is actually going to be downwards, but that is for a positive charge. This being a negative charge, the force will actually be upwards. So the magnetic force on this electron will be in upward direction. I'll write FB to indicate the magnetic force. So magnetic force on this electron, this single electron is actually going to be upwards. So I'll just draw that here. Watch this part again if you have not understood. So magnetic force is going to be upwards. So force F is upwards. Wait a minute. Actually, the electron was not going upwards. In a conductor without battery, electrons don't move in a single direction. But looks like this electron is going upwards. And this electron is not special. This is no different electron than any other electrons that you have here. So I'm thinking all the electrons that we have in the rod CD, all these electrons which are there in rod CD are going to experience force in upward direction, and as a result more electrons will sort of get crowded near C. The electron crowd gets more near the C end of the rod, and there will be a there will be a lack. There will be a lack of electrons over here. So there is more electrons near the C end, more electrons near the C end, and less electrons near the D end of the rod, due to the whole discussion that I just made. And as a result, C behaves like the negative potential or lower potential, C behaves like a low potential and D behaves like positive or higher potential, which is as good as the sort of battery we had placed a while ago, right? See this battery we had placed a while ago, this battery right here. I'll show the diagram in the actual diagram. Look at this. C is the negative potential and D is the positive potential. And notice how we took completely different approach. We went back to our very fundamentals of magnetic force, this FB, very fundamentals of magnetic force. We went back to magnetic force, and then we went back to the very basic concept of force of magnetic force on the electrons, and as a result electrons start moving up. And therefore you also know this, if electrons are moving up, that means the conventional current is actually downwards. So you can in fact show that as well. The conventional current will be in this direction, and then it goes on. So current is downwards, and I've been saying this a lot in recent videos, that electrodynamics and magnetism, they are not very different from each other. They have more in common than one would think, right? And since they have more in common than, they actually are phenomenon that create one another. We'll discuss more about the sentence that I just said in Maxwell's laws, but for now what I'm trying to say here is, can I maybe think the motion of electrons upward as electric field being downwards? I hope we remember that electrons experience force in a direction opposite to electric field. So I can in fact say that the electric field is making these electrons go up, and electric field which makes the electrons go up must be in downward direction. And this electric field right here is actually a very interesting concept. This electric field right here is called induced electric field. You must be thinking, where did suddenly electric field come from, right? It's not like electric field you have established electric field or anything. What has happened is, you had magnetic field led to the motion of electrons in upward direction. We have discussed all that, and electrons are moving upward could in fact mean that there is an electric field in downward direction, because we know that electrons always move in a direction opposite to electric field, right? And such an electric field is called induced electric field. So actually the last part of this video, like this second half of the portion, is very interesting. I've tried my best to explain things. If not, watch this portion at least again and again. You'll really appreciate this. And there is more discussion, very interesting discussions on induced electric field in next video. Alright, so yeah, I hope I have done to some extent my job to make you understand. Alright, so hope that helps. Great, thank you.